Alright, so today I'm going to show you, or maybe possibly basically something or another, I don't know, anyway, I haven't woke up yet, even though I've been awake for 3 hours. So anyways, I have this thing that I got from a fellow friend of mine, and it's a DCS 100 watt DC to DC switching converter. My interest was, if you can see this, is the input's 18 to 36 volts and outputs 13.6 volts at about 7 amps. So what's that good for? Well, connecting to a solar panel. So a solar panel's voltage is obviously going to vary from anything that's useful, producing any usable current, is about 14 volts up to 21 volts open circuit. Under load, the average solar panel is that's designed for 12 volt systems is going to output about 17 volts. So what this old time switch mode power supply does is that it takes the power in from the solar panel, feeds it through this capacitor, goes to this little trimming inductor, and then goes off to the rest of the circuits. That's the high frequency transformer. This is the monitoring circuit, and then this is the switcher that actually that takes that DC and pulses it up and ramps it up and then sends it to that transformer there. And then this is the secondary that comes out into these two posts that went into a this is a diode pack actually, and it goes out to there and it's rectified into DC, and that's what the diode pack looks like. Let's see if you can see that. Damn thing. There it is. So these two pins are the inputs, which comes from there, turns it into DC, goes to this little inductor to filter out some noise and smooth things out, and then goes to the output filter capacitors, and then finally to the output. Now the reason why I tore this apart is because that right there, somehow, some way, about a year ago, I had connected this thing up to a solar panel, was charging the battery. I left to go do some things and came back and found that my wires were melted and so on and so forth. So doing basic troubleshooting would lead me to believe that something along this path, because this side, the output, which this original output inductor was connected to, was here, and then it shorted itself out. Now, the only thing that's in its path that will cause it to short out is this diode pack right here in a TO3 case. So why that died, who knows, but obviously it did, and it shorted itself to ground. And clearly these traces, but you can still see evidence to where the circuit traces got really, really hot. So you see where it's slightly discolored. Sorry, you can't see that, but slightly discolored, and you can see that there's some serious heating here. So I don't know if this circuit's going to work, but anyways, what you get out of this is, first things first, if you're going to try to fix something and you're not really sure what you're doing, is look for the obvious. And that's what I'm doing on this one. This thing is probably 20 years old, maybe 30, given that there's absolutely no surface mount components on this thing whatsoever. This is the transistors right here. If you see transistors in a metal case right here, this is late 80s type technology. Maybe even late 70s. But anyway, switch modes didn't come out until the early 80s anyhow, late 70s. So this thing's pretty damn old and probably really inefficient, and it is, and it's really noisy. So, excuse me, if this thing doesn't work and there's other problems with it, then I'm going to just trash it and just smash it with a hammer. So anyways, what's making me give a slight glimmer of hope that this thing's worked is when I plugged it in yesterday, I was using a 19 volt laptop power supply to feed into the DC side, and open circuit voltage was about 13.7, which that's what I had set it to when I first got it anyway. And then I plugged it in again yesterday, yesterday, see what it was. But as soon as I plugged in, the little green light for run came on. But as soon as I plugged in a battery, a little orange, the red light came on, telling me that it was overloaded. And when it's connected to a solar panel, yeah, that battery can potentially draw a lot of current, but it's only going to draw what it is given. So there's no possible way to overload it. So if the power supply is rated for 2 amps, then that's all it's going to pull. You know, that's one of the designs of this thing, is that it's only going to supply enough current to keep its input voltage high enough and not drown itself out. Anyway, so let's put it back together and we'll see what it does. Okay, so it's put back together. I did this to replace the original TO3 diode pack with a, whatever that nomenclature is for that. Anyway, it's got the isolation and stuff in there, little pad in there. And then I rewound, I found a toroid core in my box of parts that came from some sort of electromagnetic interference suppression. Replaced capacitors, and again, same power supply, a little 19 volt, 2 amp hour deal. I measured the current right away. It's drawing 1.1 amps-ish, and it's 86% efficient. So I measured the current that the battery was drawing, and there's a wire. And then I measured the current that the device itself was drawing to see what the inefficiencies are. But anyway, there's a bigger toroid core that I had stolen from original computer power supply before they got cheap Chinese on us. And this is also an EMI suppression deal, because as awesome as this thing is, and as you can see it is working, the overload light is not on. See that it is on there, but the overload light is not on. But the bad thing about this thing is, because it's a significantly older design, its EMI and radio frequency interference, or RFI suppression, is relatively poor. So I'm going to have to do some other things, because as soon as I connect it up to the high frequency radio, it makes all kinds of noise. It's really, really hashy. And it's like I said, it's just because of the design. I don't know what frequency that is, but we can find that out. So matter of fact, I'm curious. So let's see exactly, if we can, what the switching frequency of this thing is. So looking at the meter here, the switching frequency, according to this Craftsman Miniscope, is, let's bring the light here, is approximately 54 kilohertz. And you see what it's doing. So it's pulsing. Of course, I got plugged in backwards like an idiot. But you see that it's pulsing on and off. That's how it works. Is that the transformer, the switching transistor right here is pulsing this transformer at 54 kilohertz, which is relatively low by today's standards, because today's standards you're looking at about 150 for the lower end. The newer model, lower end, to almost 500 kilohertz in switching frequency, which is significantly easier to filter out, as well as you get even smaller transformers. But anyways, that transformer is producing a 54 kilohertz signal that is getting rectified by the diode pack there, going through this inductor to filter out some of the noise, as well as also level it out, going through the output capacitors, and finally its output. So now let's see what the output is on the power supply with load, and then we'll see what it's like without the load. So with the load, it's relatively clean. Supposedly it's not detecting anything, but like I said, the battery acts like a really big capacitor anyhow, and it's reporting very clean. But you can see every now and then, as the meter changes its time divisions, you'll see that some little products come up every now and then. So that's measured in DC. Let's see what it's finding on the AC side. And there you see it. It's on the the meter is now measuring AC, and you see that it has about 26 millivolts of ripple voltage. And you see some little nubs here and there. So there is evidence of switching products still in the output there. Now, of course, it's high frequency, because you see that it's 10 microseconds, which is equivalent to about 10,000 hertz, if I've done the math right. That's what I wanted to see. So you see that it's detecting it right there at 320 microseconds. You can see that it has it ranges anywhere between 710 hertz. Oh, and you see that as the battery is getting more and more charged, it seems the pulsing frequency is getting more and more prevalent. So let's see what it's like without the load attached. So it's just going to be measuring open circuit. So open circuit, this thing does about 13.6 volts, which is what I had set it to. Now let's see what the output is on AC, if anything. And it has, you see right there where it says 118 hertz. Oops, wrong button. Get out of that. Okay. You see that still has, again, about 25 millivolts of ripple voltage. And then we'll see what it does. Like I said, it's got, you'll see the evidence of switching products in there. There's a little bit of slight, but not too bad. So anyways, what you can take away from this video is when you're fixing something and troubleshooting it, is there are a couple things you need to know. First things first is you need to know what the device was doing, how it's supposed to work. Okay, you need to know what, at least the basic stuff. I mean, obviously it's going to be just next to impossible without reading schematics and stuff like that to know exactly how the thing works in its actual connected fashion. But what you need to understand is how the thing works, at least in a logical layout and a logical block diagram. So it helps to have a whiteboard. Say, okay, the input goes into this circuit, it does this, it goes through this process, and then finally it's outputted here. So that way you can start isolating sections as to what may be bad. Another thing is to keep really good notes on what you're doing and what your observations are, so that way you don't go back and double check things. The other thing is make sure you know how to use your damn meter and what it's telling you. I mean, yeah, it's nice to have all these toys and stuff like that, but if you don't know what your meters are telling you, you know, yeah, you might see some numbers, but if you don't understand what those numbers mean, especially in the process when you're measuring things, then you know, that doesn't do you a whole lot of good. And then, like I said, it helps to spend, you know, 15 to 20 minutes looking at the device, just kind of figuring out how things are connected, figuring out the logical layout. Like this particular part right here, I don't know if you can see this, but this is a UES 2603. And wasting an hour of my life Googling and trying to find out what it is, I could not. It's just because this thing is so old, that part is not used. But like I said, through logical deduction, okay, the output of this transformer goes to these two wires, which this is a secondary, and then lifting up to the board, they went to these two pins, here and here, were the inputs, and then this was the output. You know, the actual case is the output. So if this was a transistor, that means the collector was the output, and the base and emitter pins were going to be the input, which transistors do not work like that. That's not their function. You know, yes, you can use them for switches like that is, but the base pin is normally what's driven to switch it on and off. But obviously this was not the case, because the two outputs from the high frequency transformer were feeding these two pins, and as you see the diode pack there, you see that it's just two diodes that have the anodes connected together. Anyways, it goes to the transformer there, or the inductor there, and then just following the circuit traces, you'll see that it goes to the output filter caps, and then finally through the output. The other thing is, if you have manuals, know how to read your manuals. That's another big thing for troubleshooting. But anyways, yes, it's a long video, but if you watch it entirely, troubleshooting is not a short process. It does take a long time. After a while, you can obviously tell that when you're spying with your little eye, that if you see a part like this that does not at least used to look like this, but now it looks like this, is like, okay, something really bad happened. And in terms of power supplies, one could reasonably assume that something in there shorted, in which case the original diode pack did exactly that. Thanks.